he called elastic sediment. Usually, the elastic sediment for soil, especially for fine-grained soil, is supposed to be very small. And then the stage 2 would be primary consolidation sediment, which means here will be the major sediment occurred once the pore water pressure dissipates. For example, the loading can be replaced as a pumping. The loading, the purpose of loading actually is to squeeze the water from the soil. Once the water dissipates, the consolidation starts to settle. And the last stage, stage 3, we call it the settlement consolidation stage. This used to be the result of plastic adjustment of soil fabric. So, if we understand the pore water dissipation process, then we will know once the volume change in saturated cohesive soil, the water released from the soil, then the consolidation sediment occurs. So the control of groundwater pore water pressure dissipation is the most important things to stop soil consolidation. Another thing is very also important is the drainage path, the length of drainage path, which, for example, here is the fine-grained soil layer, the thickness of the fine-grained soil layer. The HDR, if the HDR is long, is very thin, or the value is very big, the drainage of pore water pressure will take more time, which means the settlement will not easy to occur. So it depends on the soil combination in our different areas. And in this study, we first derived the solution of the Terzaghi consolidation equation. The previous slide, what I demonstrate here, we have a governing equation. We call this the Terzaghi consolidation equation as here. It's actually very similar to diffusion equation, one-dimensional diffusion equation. But in soil mechanics, we call it Terzaghi consolidation equation. Also, in this study, we try to derive a more general exact solution of this governing equation by using some mathematics operation, okay? And this solution actually is more general than the textbook, which has the exact solution in the textbook. We have more general equation, which you can consider different boundary condition of the upper bottom side. And once we know the dissipation of pore water pressure change, then we can compute consolidation or the settlement of soil layer. Okay, then we go into the field. This is the WI borehole logging. In the Yunlin County, we have about 24 borehole, which have very detailed investigation data. This left figure, as we can see, is the direct from the logging data. We can see under the ground, the soil combination actually is very complicated. We have surface soil, we have gravel, we have coarse to medium sand, we have fine to very fine sand, and mud, silt, and mud, this one. First things we are going to do is to convert this kind of different soil description into a soil type. Because in soil mechanics, we have already divided the soil type, which is gravel, sand, silt, and clay. But in this study, we have 6 different kinds of soil type. And then we convert the soil type into aquifer and aquita. As I just mentioned, the aquifer actually is water-bearing. layer. Aquitard will be the settlement layer. So the green color is the aquifer, and the red color actually is the aquitard. As you can see, from the regional point of view, in the Yunlin County, we have 4 aquifers. But once you look into the borehole data, it's difficult to say we have 4 aquifers. So precise soil consolidation model has to be established first. Once you establish a precise soil model, then you can use the Gamma equation, the solution, to model and to compute the settlement. And here, the central figure is the previous study. They use the regional aquifer, 4 aquifers. As you can see, the primary consolidation layer, this borehole actually is in Tuku. It's the most serious landslide area right now in Yunlin. The major consolidation layer actually is behind 250 to 300. If you use the aquifer, 4 aquifer system, the regional aquifer system, you cannot easily to say here we have major consolidation layer, because here is the aquifer, not aquitard. But if you look into the borehole data, you can use our classification system. You can see here we have some kind of multi-layer soil system. Also, we have many aquitard in here. The aquifer syncness actually is good, is sync enough. So by here, we also compute the consolidation settlement for different kind of soil. From here, we have gravel, we have sand, we have silt-driven clay. Then you can see the major contribution for the consolidation or for the settlement actually will be from silt and clay. For gravel and coarse sand, for 25 years time span, you cannot get a lot of consolidation. So, which support our aquitard system will be the main consolidation layer. And then we use the same technique to compute different borehole data to fit the deformation. And you can see this kind of procedure can easily to obtain reasonable consolidation result. From this side is the monitoring data, this is our study, and also this is for another side, this is our study. So you can see different borehole show different characteristics. For example, Tuku Guozhong, the borehole demonstrate like the major consolidation is from very deep, from more than 220 meters, which means we must have a deep well pumping in here. Otherwise, there is no possible to have settlement this deep. Sometimes we have thinking about the agriculture, but agriculture, the well for the agriculture usually will be very, very shallow. We believe is about 50 meters. So the agricultural well is supposed to be not possible to have a consolidation in such a deep place. Must be some deep well in here. And this totally show different trend. As we can see, this is the Xingang, Guoxiao, in Zhanghua County. There's a settlement majorly occurred at the 150 depths, okay? And another side, we're doing the same thing. We can find all the simulation with the majorly, with monitoring data fit well. And finally, I will give you some introduction about the geospatial layer preparation. It's kind of using GIS. We have investigated all the data from WRA and from the government. So we can establish a database, and using GIS, we have the cumulative subsidence map, blah, 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 and the agricultural well map. This is all for agriculture. Thousands, hundred thousands well actually in this area. But what I said is all agricultural purpose, is all shallow well. We also have to investigate the deep well as well. And here is the also the synthetic make for the what I talk about HDR is the length of maximum drainage path. And here is the fine soil content. And this slide is the cumulative subsidence map. As we can see, Tuku area is the most serious land subsidence area. And also, it's very highly connected with fine soil content. Also, connected with the length of the maximum drainage path here. So some people may say, Professor Gu, there's also have many fine soil content in here, but here there is no sediment because the drainage length in here is not quite different. Okay, finally, I will skip the theory of principal component analysis. I just show you our study to connect and to identify the major soil layer for the land subsidence. As you can see, we use 27 WRI borehole. We make the PCA analysis. We can find the major contribution of the land accumulate subsidence value is which is the soil layer, silt and clay, and also silt. But in this area, we hardly find the clay layer. So most of the fine-grained soil is the silt. Another PCA using 102 borehole, we also obtain the same result. And finally, I would like to give it my conclusion. So the long-term overuse of groundwater may be the major factor causing regional land subsidence in our study area. In this study, we use various methods, including the soil consolidation theory and the GIS, and also PCA. Results demonstrate that the land subsidence especially in the Yunlin area, which is mainly from the aqueduct. The soil composition of the aqueduct actually is a fine-grained soil, which is a silt. The silt, we can say it's a silt because we're using a PCA analysis. The result also demonstrate the silt is major soil layer contribute to the land subsidence in the Yunlin County. Future study, we believe, have to be launched to give an inside view, including the contribution of different aquifer systems to land subsidence. Especially, we want to find the deep well, the location, spatial distribution of deep well, the hydromechanical behavior of the aqueduct, and the regional scale simulation of coupled groundwater flow and aquifer system deformation. That's all my presentation. Thank you for your attention.